Have you ever wondered what happens to the electricity from your wall socket before it powers your sensitive electronics, and why a smooth, steady flow is so important? Imagine trying to listen to music or run a complex calculation with an unstable power source. Achieving that clean power is a key challenge in electronics design. The most effective and common way to reduce ripple voltage in a bridge rectifier circuit is by adding a large electrolytic filter capacitor in parallel with the load resistor. This capacitor acts like a temporary energy reservoir, continuously charging and discharging to smooth out the rectified direct current output, making it much more stable. Ripple voltage is essentially the small, unwanted alternating current component that remains after the alternating current input has been converted into pulsating direct current by the rectifier diodes. Without filtering, this pulsating direct current would be unsuitable for most electronic devices, causing instability or even damage. The capacitor works by rapidly charging to the peak voltage of the rectified waveform. Then, as the rectified voltage drops, the capacitor discharges into the load, maintaining the output voltage at a higher level than it would be otherwise. This continuous charging and discharging action effectively fills in the valleys of the pulsating direct current, leading to a much smoother output. The extent of this smoothing depends on the capacitance value, the load resistance, and the ripple frequency. When selecting a capacitor for ripple reduction, choose a component with a sufficiently high capacitance value. Generally, a larger capacitance results in less ripple. You also need to ensure its voltage rating is well above the peak output voltage of your rectifier. Another important consideration is the capacitor's equivalent series resistance, or ESR, which affects its ability to store and releases energy efficiently. Full-wave rectifiers, like the bridge rectifier, inherently produce a ripple frequency that is double the input line frequency, such as 100 or 120 Hz. This higher frequency makes it easier for the capacitor to filter the ripple compared to a half-wave rectifier. For applications requiring extremely low ripple, you might also consider adding an inductor to form an LC filter or integrating an active voltage regulator circuit. The effectiveness of ripple reduction is often quantified by the ripple factor, a metric that describes the ratio of the root mean square value of the alternating current component to the direct current component of the output voltage. A lower ripple factor indicates a cleaner power supply. Achieving a low ripple factor is paramount for sensitive digital circuits, audio amplifiers, and radio frequency systems, where even small voltage fluctuations can introduce noise, errors, or affect performance. There is always a trade-off between the desired ripple reduction and the physical size and cost of the capacitor or more complex filtering components. Ultimately, reducing ripple voltage is about ensuring a stable and reliable direct current power supply, which is the lifeblood of almost every electronic device. By strategically employing filter capacitors, and sometimes more advanced filtering or regulation techniques, we transform raw alternating current into the clean, consistent direct current that allows our electronics to function precisely and dependably, ensuring optimal performance and longevity.